supervised and unsupervised tasks. Supervised tasks being tasks with a label that we know the ground truth is, what the ground truth is. And unsupervised tasks are mainly clustering documents together or trying to generate text in which there is no ground truth. There's no one true way, one correct way to do the task. An example is topic modeling. For example, I have a lot of documents and I want to cluster them together. Text generation, mostly used for search engine optimization. And in the supervised domain, we have text classification, which is the topic for today's workshop. Sentiment analysis, which is mainly whether a tweet was positive or negative, whether the review is positive or negative. Name entity recognition, and machine translation, which is kind of in the middle between supervised and unsupervised. Meaning that we have a label, but we have more than one way to translate a sentence. Okay, this workshop wouldn't be complete without talking about why Hebrew sucks for NLP. So, Hebrew is a Semitic language which is really not fun for those who are trying to process it. First of all, we don't have vowels, so you can't really read it without nikud. So it's really hard for an algorithm. And tokenization being the process of separating a document into words, is really not trivial in Hebrew. I guess that most of you know that Neta won the Eurovision, and after she did, there's this warm congratulations from our Prime Minister saying, Neta kapara mitit, which being translated into Neta, you're a real cow. Now, I don't blame Bing, because tokenization in Hebrew is a real pain. So, kapara, for those who don't speak Hebrew, can be tokenized as a cow or cow-like. So, even the great Microsoft fall for this problem. Okay, a little bit about our data set for today. I assume that all of you already downloaded the data set from this link and cloned the Git repository from that link. Our data set for today is approximately 4,000 contracts with 6 categories, mainly bylaws, employment agreements, registration rights agreements. You don't have to be a lawyer to understand, to classify those contracts into the right label. And I tried to match each slide here with the Jupyter notebook that is most relevant. So this symbol means that the slide carrying this symbol matches with Jupyter notebook number 1. And so goes on for 2 and 3. We'll follow this text specification workflow for the slides. Each process, we'll talk a bit about each process, and then we'll elaborate a little bit more about two machine learning models for classification. So all of this process takes us from a document into a vector, and here we take this vector and train it using a machine learning algorithm. So starting with reading the documents. So the first notebook talks about pre-processing, in which we take the raw document. In the examples, you can see that I remove all the punctuation, all the text is in lowercase. Numbers, for example, in most cases, you don't care whether the client pays $500 or $5,000. I only care it's a number in order to classify the contract. So you can see an example of replacing number tokens with the token num in triangle parentheses. I suggest to try also other pre-processing. For example, there are a lot of companies over there. You might want to try to create a company token. For example, West F Inc. or Ltd. It's pretty easy with the regular expressions. You have examples over there. Another thing that repeats quite a lot in the documents is enumerations. You might want to replace it with your own token. More advanced types of pre-processing might include identifying phrases. Now, this is not mandatory by any means, but you might want to identify phrases, for example, New York. The word new and the word York are not that informative on their own, but the combination, the phrase, might be a bit more informative. So there are examples about how this can be done with NLP and GenSim at the end. After we pre-process the data, we go through by tokenizing. Again, tokenizing is taking the entire document and splitting it into words or tokens, more generally. There are a lot of ways to do tokenization. We will focus on the most simple one, which is splitting by white spaces and punctuation. You can think about something more intelligent. For example, girlfriend might be split into girl and friend. And in other languages, for example, German, this is mandatory. We can live without it for the purposes of this workshop. Okay. Now we have a list of tokens. Our next stage is to try and apply stemming and counting. Stemming is a way of transforming a word into its root form. For example, I have here all the inflection of the word going. After being stemmed, I have go, gone, go, and went is not being stemmed. Stemming is a mechanical algorithm. It doesn't know whether the word is in the vocabulary, what is the right answer. It just tries to add and to remove suffixes and prefixes. Lemming or lemmatization, on the other hand, takes into account the vocabulary, so it can do more intelligent things. For example, to know that the root form of went is go. On the other hand, if there are words that aren't in the dictionary, then the lemmatization won't do anything. There are three main stemmers in the NLPK library. I suggest you play with them. I think that the most common is the Porter one because it's the fastest and simplest. And there's one lemmatizers, the WordNet. Okay. Our next step is to define what is the vocabulary we care about. So there are a lot of words in the corpus. Not all of them are important for classification. One way of doing that is looking at the frequency of words, assuming that very rare words are not informative. For example, names of clients, customers, places that you hear only once in the other data set. And very frequent words may be stop words. For example, the, of, therefore, and other words that, again, aren't very informative for classification. So there are two ways of removing stop words. One is by filtering the frequency, just saying that we care about words within some frequency range. And another way is to give the predefined list. And again, NLPK and sklearn have the list of all of the stop words in English. So it's already implemented for you. Okay, so here, for example, we remove all of the red words. Okay, our next step is to take the tokens, the stamped tokens that we have after filtering and building and generating our vocabulary, and converting a document into a vector. One of them, I think that the simplest way is to count. So, assuming that I have this document, the quick brown dog jumps over the lazy dog. I tokenize them. Then I remove the stop words, V and over. Jumps turns into jump after stemming. And then I count the occurrences. So here I have a vector of size 5. But is it size 5? Actually, it's the size of the vocabulary, where all of the other possible words have 0 values. So this one-hot encoding really depends on the size of the vocabulary we chose. The same trick can be applied also for pairs of words or bigrams. So let's say, for example, that I consider the vec width to be one instance in the vector. I can apply the same logic, but I will have a vector of size of the vocabulary square. Okay, so this is how you calculate bigrams in Python. I know that everybody loves one-liners in Python, so there you go. Just one-liner with the zip function. And the counting and the rest is the same. The one-hot vector embedding is very easy to interpret, but we don't have to use counts in the vector instances. For example, we might want to use indicators, whether the word appears or don't appear in the document without caring about how many times it appears. Another technique that we'll elaborate a little bit more is some kind of weight. For example, maybe common words such as the, of, or stop words, or very interesting words I want to weigh in a different way. A general way to do it is PyData, that we'll elaborate in a second. And another technique is to convey location or styling information. For example, I might consider words that appear at the top of the document to be more important than words at the bottom. Or words that appear in bold. In our workshop, everything is without styling. But if you process a web page, you might want to consider words that are headlines or bold to weigh more than other words. Another way to do word vectorization is called word2vec, which I think it's pretty much a buzzword currently. The motivation behind word2vec is to encapsulate some kind of information from the surrounding words. So let's say I have this sentence: the capital of blank is blank. As humans, we know that the first blank is supposed to be some sort of country, and the second blank is supposed to be some sort of city, hopefully a capital city. So word2vec tries to encapsulate this information and have similar words, or words that can appear in similar contexts, to have similar vector representation. This is really a gross simplification of word2vec model. This is not, the details are completely wrong here, but it demonstrates the motivation. So, assuming that I look 2 words before and 2 words after my target word, and train a model to predict the word in the middle. So, for example, capital of blank is London. I apply some kind of deep learning magic and a lot of details that I'm not going to go into right now. And I'm going to get a vector representation of the word England. Now, the vector representation that I'm going to get is typically very small and dense, unlike the one-hot encoding, in which the size of the vector was the size of the vocabulary, or the size of the vocabulary squared, and the common vocabulary is approximately 200,000 words. There are 200,000 words, give or take, in English. So the size of this vector is going to be between 50 and 500, no more. It's a parameter, but it's very small and dense. If you apply this technique, you get some interesting properties out of it. Okay, there are other ways to do embedding, just Google them. Fasttext and Glove are other ways to do similar dense embeddings. But in word2vec, an interesting property arises. For example, if I take the vector of Paris, subtract France, and add Italy, it's going to be pretty similar to the vector of Rome, which is interesting. So you can solve your analogies next time you do psychometric tests. No talk about the word2vec would be complete without this example of king minus man plus woman is approximately queen, which really is amazing and unexpected. Okay, so we have 2 ways of vectorizing documents into words. One way is to count or weight or PyData, which we'll talk in a second. And the other way is to take those predefined word-to-vec representation. I have trained word-to-vec for you. You already have the list of each word and its representation. It's available in the Google Drive. And weight them accordingly into the document vector. So we talked a bit about the values in the one-hot presentation. PFIDF is a way of punishing words that are very common. Basically, we divide by the amount of time that we see them. So very common words are going to have less of an impact, and very rare words are going to be more impactful. Typically, the calculation is done in logs because of numerical stability. Okay. We covered so far how we take a document and convert it into a vector. Next, we're going to cover two models about how you take this vector and train it against your target label, deployment, registration right agreement, etc. So